Hello everyone, I'm Arjun and today I'll talk about the impact of commodity networks on storage disaggregation with NVMe over fabrics. This is a joint work done with Shashank Gugnani and Xiaoyi. So to give an outline of the talk, first I will discuss about the overview of disaggregated storage and NVMe over fabrics, followed by our characterization methodology, testbed and results. In the end, I will talk about our conclusion and future work. So direct attached storage is one of the earliest architectures of storage disaggregation. From the figure on the left, we can see that each compute server has its own disk storage attached. The advantage this offers is the high performance for any workloads running on that server. But this leads to low capacity utilization as the cloud providers will generally over-provision storage to handle peak capacity. The next architecture was storage area networks. Here, disks were pooled and made accessible via the networks. This allowed many devices to draw from one capacity pool and increase the utilization across the enterprise or data center. This reduces the management overhead as one does not have to manage many storage silos. But the main disadvantage was that specialized networks needed to be laid down to ensure lossless and high-speed nature. Previously, SATA SSDs were used in storage area networks, but SATA was designed primarily for interfacing with mechanical hard disk drives and needs a host adapter to communicate between the CPU and the disk. And with the emergence of NVMe SSDs, non-volatile memory express is used as a communication interface and a driver to allow CPU to directly talk to PCI-based SSDs. So the advantage of using PCI for interfacing with SSDs can be seen from the figures with high throughput and low latency. This is possible due to the high bandwidth provided by the PCIe. Again, NVMe is the standard interface for PCI SSDs. It has up to 64 IO queues with up to 64K command per queue, unlike SATA, which allows only one command queue and up to 32 commands per queue. This significantly reduces the IO overhead and provides low latency and parallelism. With the advancements in storage media and with the emergence of new media like non-volatile and persistent memory, the network overhead is quite comparable to the storage media access time. Now the goal of storage disaggregation would be to use commodity networks without having to lay down specialized networks as we did with SANs. With it, cloud vendors can not only have storage efficiency but also have the flexibility to upgrade and scale storage capacity as required. The next question would be, is storage disaggregation possible? Because we saw earlier that storage IO overheads has reduced over the years. And the answer is yes, because there are a number of networking technologies like Ethernet, Fiber Channel, and InfiniBand which can offer high bandwidth and low latency for applications. Due to the fast interconnects and low storage access latency, network overhead constitutes a significant portion of remote access latency. Thus, it was not beneficial to study the impact of network protocols until now. And it would also help cloud vendors to deploy networks by knowing the characteristics and trade-offs of different network protocols used for remote IOs. This is the gap we would like to fill in from our work. Let's talk about NVMe over fabrics. It is a newly proposed protocol that allows remote access to SSDs over the network. The important fabric is RDMA because it provides low latency and has one-to-one mapping of NVMe IO queues to RDMA send-receive queues. Because of this, NVMe over fabric architecture is able to achieve low latency overhead compared to local IO. We use Intel's SPDK library to analyze various transports as POSIX NVMe has high software overhead and also the context switches for every IO call. In contrast, SPDK provides user space, lockless, pole mode components which provide significantly lower latency and higher throughput. For our evaluation, we use 4 dimensions to characterize NVMe over Fabric's performance. Network protocols like TCP/IP, RoCE, IP over IB, and IB. Then workloads like sequential, random, and mixed read-write workloads, IO size, and the number of cores. Our testbed mainly consists of two servers which are directly attached, and each server is a two-socket 28-core Intel Broadwell CPU and has an Ethernet NIC, a Rocky NIC, and a IB EDR NIC. And one of the servers also has Intel NVMe SSD, which acts as the NVMe over Fabric target. The metrics which we uh, evaluate on are bandwidth, latency, CPU utilization, and SSD concurrency. So first let's see the variation in bandwidth with respect to IO size. So in the figure, on the x-axis, we vary the IO size from 1 KB to 1 MB and study the variation in bandwidth for four different network protocols. So we can see that small IO size such as 4K is sufficient to achieve near peak bandwidth for all transports except TCP. Next, we study the variation in throughput with respect to the number of cores for 4 KB random read IO. Again, for network transports like TCP, Rocky, and in IB, the bandwidth does not change or depend on the number of cores, unlike IP over IB, which needs at least 4 cores to reach its peak throughput. Now let's see the variation with respect to workload at full subscription. So we evaluate on 6 workloads for two IO sizes which are 4 KB and 1 KB for all the four networking protocols. The random read workload generates the highest throughput, and the write throughput for all the network transport is limited by the SSDs. Now let's talk about the latency. So we can see that for 4 KB and 1 MB random reads IO, the average latencies for the networks is quite comparable to local SSDs. So this shows that NVMe over Fabric adds minimal overhead. Also, the P99 latency for IP over IB for a 4 KB random read IO is approximately 2.5 times that of provided by the IB. But surprisingly, as we increase the IO size to 1 MB, we see that the tail latency of IP over IB is 13% lower than that of IB. Similar to how we saw the number of cores affecting the bandwidth, now we want to see how the latency is affected. So clearly, for all the transports, the latency increases as we increase the number of cores. Also, for small and medium-sized I/O, the tail latency of IB is far lesser than IP over IB, but as we increase the I/O size, the IP over IB has much lower tail latency than IB. Next, we talk about the CPU utilization to measure the efficiency of the transport types initiating I/O at the client. Clearly, TCP and IP or IB have low user mode CPU utilization compared to the polling-based Rocky and IB. This shows that polling might not be good for IB at large IOs, and rather event or interrupt-based mechanisms should be used. Next, let's discuss about the SSD concurrency, which is nothing but the amount of parallelism of each transport type. And we compute this by dividing the throughput by local NVMe SSD throughput at a queue depth of 1. So clearly we can see that IB achieves a higher parallelism for both sequential and random read workloads at a 4 KB IO size. So finally, to conclude, we have done a 4-dimensional evaluation of NVMe over fabrics across network protocols, number of cores, IO size, and workload. And clearly, native RDMA with IB was able to deliver the best performance in most of our experiments. And contrary to popular opinion, IP over IB gives the lowest tail latency and CPU utilization at large 1 MB IO size. Also, single core was sufficient to reach maximum throughput for Rocky and IB for 4 KB IO sizes. In future, we would like to study additional protocols like IORP and fiber channel, and also the different type of NVMe SSDs. And we would also like to evaluate on key value stores and distributed file systems. Thank you.